Welcome to this lecture video. We're going to look here at optimization applications for pre-calculus using technology. We looked at some of the applications and things we can do with our calculator in our previous lesson, and we've been practicing seeing some of those things and exercising some of those things in the exercises you've been doing in the worksheets up to this point. Specifically, we want to look at some application problems where we actually would do this type of thing. So, for example, there's a lot of applications that require that we find either a minimum or a maximum quantity that will satisfy certain conditions. Automobile manufacturers may want to design an engine that will have a maximum fuel efficiency. And so there may be a maximum fuel efficiency variable that's relatable to size of the engine. And so they could produce an equation where we could actually find a maximum fuel efficiency, which is really finding a minimum amount or using a minimum amount of fuel. A cereal box manufacturer might want to design a cardboard box that will contain a fixed volume, but would require the least amount of cardboard. And so we're going to look at how we can do this as kind of in a preemptive way, because we're going to learn the hows and whys, the mathematical hows and whys when we get into calculus. But there are technological ways that we can do this now. So first of all, let's just kind of review how we can do this using technology. And so we're going to look at just an equation where we're given a very specific direction here. We're wanting to find the highest point or the maximum. We call it a local maximum for this equation in between -3 and +3. So on our graphing calculators, we're going to go into y equal to and type out this equation into the y equals. So that's 2x to the third power minus 3x squared minus 12x and then +1. And we specifically want to look between -3 and +3. Now, when I graph this, I'm simply just graphing a standard window, -10 to 10, -10 to 10. And you could see that if we want to hone in a little bit more on this, we could adjust our window. We notice we would need to go a little bit further down on the y-axis. And then I could probably hone in a little more on the x-axis. Since we're only wanting to find it from -3 to +3, we can do that in our x's. And then our y minimum, we wanted to go a little bit lower. So I'm going to lower that to 20 and see if that's going to be helpful to us. And then we can hit graph again. And we still didn't go low enough for that. So, and actually this, for some reason, isn't liking it when I type it in. So I'm actually going to type it on my calculator here. Oops, but we need a negative there. So we're going to put -20 there. And there we go. That's a little bit better. What we were looking for is the highest local point. Now we know that this continues to go up. And so that's why they've limited us between -3 and +3. We know that locally, this would be the highest point. So from this point, we're going to go to the calculate functions, which are above trace. So if I hit shift and then calculate, which is really taking us to we're hitting shift and then trace, which is taking us to the calculum. Then we go to choice number 4. Now your choice number may be different. I believe on the TIs, if I look it up right now, it's the same choice number, choice number 4. So we're going to hit maximum. And then it takes me over to the graph. And here I need to tell it where to have a left boundary. And so we're going to, you probably already have a blinking thing. So you just want to use the arrow keys to kind of move it to the left of the peak that you're after. So you'll see down here, it says left boundary. question mark. So just move it somewhere that's to the left of it and then hit enter. Then it asks for the right bound. So you want to use your arrow buttons over here to move that around until you're to the right of that point somewhere. It doesn't really matter. And then it should actually, for most calculators, I believe it says guess or something to that effect. So you have to hit it one more time, hit enter one more time, and it should take you to the peak here. And we see that our peak is at -1, +8, a very specific point for this particular function. Sometimes it may give you something with decimals. If it looks highly rounded, like if we had 0.9999999 or something like that, you can usually round that. The calculator sometimes is a little bit limited in that way, but when it's a whole number, sometimes it'll give you a, here it is very specific, but I think the calculators don't quite work as well. But this is my local maximum, -1, +8. I may have said +1, but it's -1, +8. And that is how we can find our maximum. And the same thing would be true for a minimum. If I go to Shift Calculate, and we want to find a local minimum, your cursor just needs to move to the left of it first. So left bound, hit enter, right bound, toggle over. So you get to the right of it, hit enter, and it will give you a local minimum at x = 2. We're at -19. Well, it's really nice when they give us the equation for us to use. And on many of the problems that you will work in this section, that's the case. They give you the equation, and you've got to just find a window that you can see it in. And we're going to practice doing some of that. But other times you have to build those equations, and this is one of them. We're told that a coffee shop currently sells 440 lattes a day at $2.75 each. They recently tried raising the price by 25 cents per latte and found that they sold about 50 fewer lattes that day. And so the question we start off with, assuming the number of lattes they sell in a day, N, is linearly related to the sale price, P in dollars. Find an equation N as a function of P. So with this information that they gave us, we want to try to find a linear equation given this relationship that they've given us, where 440 lattes a day was what they sold when it was $2.75 each. And then when we increased the price by 25 cents, the quantity that was sold went down by 50, right? So we're going to use those two things as ordered pairs for N and P, where P is going to be my price, N is the number of lattes. We're going to create a function or an equation where we have N equal to, and then all our stuff for P. So for this problem, I'm going to look at these relationships. $2.75 was related to selling of 440 lattes. And then when we increased the price by 25 cents to $3, that was related to the selling of 390 lattes. So I'm going to treat these as ordered pairs, where the number of lattes seems to be controlled by the price. So X, being my independent variable, seems to have an effect on Y, which is the number of lattes. And we'll look at these as ordered pairs. They decrease by 50, so that's where I got 390. Remember that we, with the point slope formula, if we have a point it passes through, and if we know the slope of the line, we can actually, by plugging it in for x1 slope and y1, picking one of those 2 points, we will have, by plugging those in, the equation of the line. And we were told this has a linear relationship, so that's what we were wanting to find. First, let's figure out the slope. We know the slope is the difference of my y's divided by my difference of my x's. So I'm going to go 440 minus 390 on top. These are my y values. And since I started with 440, I have to start with 275 on the bottom. This will go to the, keeping that order correct, keeps the sign correct. 440 minus 390, we know that has a difference of 50, and then 275 minus 3 gives me negative 25 cents. And 50 divided by negative 0.25 is actually negative 200. So my slope is negative 200. Picking one of these two, and you can pick whichever one you want. Maybe we'll pick this one because it has a whole number 3 for the x. I'm going to plug these in now. So y minus 390. Doesn't matter which of those two you pick. And then x minus the x value there was $3 or just 3. But 3 was a little bit easier for me to work with than 278, so that's the only reason I picked it. And we simplify this out. So negative 200x. And then negative 200 times minus 3 gives me plus 600. And then to solve this for y, I finally just add 390 to both sides. So the equation of the line that reflects this relationship is negative 200x plus 990. So this is the first part of our problem. Okay, and so, sorry, I'm going to pause this here while I make a correction. Okay, and here I went ahead and put this linear equation in there, but I needed to substitute, and I should have actually done this on the screen I was working because I used X and Y. I actually had meant to put instead of Y, N for, because that's the thing we were using here, N being the number of lattes, P being the price. So I had N for Y and P for X. But this is my linear equation. The second part says now, revenue, which is the amount of money a store brings in before costs, can be found by multiplying the cost per cup, well, that would be our price, P, times the number of cups sold. Well, number of cups sold is my N. So using P as my sales price, use the equation from above to write the equation for the revenue, R as a function of P. So with this equation that I have, I want to write a new equation, which is going to be my revenue. And revenue is equal to the number of lattes sold, which is N, multiplied by the price of each latte, which is P. But we don't want to have two different variables. We want this in terms of just P. And since I know what N is equal to here, this is what the N is. I'm going to substitute N out, negative 200P plus 990. This is N, number of lattes, in terms of P. And then we multiply this by P. Distributing that, of course, I get negative 200 P squared plus 990 P. This is my new revenue equation. So there I have my new equation, which is now my revenue equation. And so then we'll go on to the last part here, C. It says the store wants to maximize their revenue, make as much money as possible. Find the value of P that will maximize the revenue. We're going to round it to the nearest cent. So now I need to use my calculator. And so we're going to pull that out. And we're going to go ahead and type this into the y equal to negative 200 x squared plus 990x. If we're using our standard window, we're probably going to run into problems here. We're just going to go ahead and pull that up. You can see here that with the standard window, I can't even see anything. It's probably because it's all off the screen. So we need to adjust our screen to be able to see this. This is a quadratic equation, so, and it's got a negative in front of it. So that tells me that this is going to be an upside down parabola. And so I need to get this into the hundreds. Just looking at what I have there, I can see that there's going to be quite a few. So I'm going to adjust my window here. And we're going to take it from, I know that, first of all, as far as my sales go, P is the price. I can't charge more. So P is my X, right? I can't charge more than 0 or less than 0. And 10 might be a little much. And then since my R is my revenue, so this is my Y-axis, I know that I don't want to go below 0. So we're going to put 0 as the maximum there. And then as far as the maximum revenue, let's just put it up to 1,000 or maybe even 10,000. Let's see if 1,000 works. I'm going to hit graph. See if we see anything. And there it is. Okay, it still needs to go a little bit higher. So I'm going to change that window, get it a little bit higher. Maybe we'll take it up to maybe 2,000. Excuse me. So I'm going to go back here. Let's change this to a 2. Sometimes if I type it on my keyboard, it doesn't quite recognize it. And so there we go. Good. So basically, we want to adjust our window till we get something that's visible for us. And then we just want to figure out what is this ordered pair here. This ordered pair here should tell me what the maximum revenue would be, R, for a given price, P. So we're going to go to calc. We're going to go to maximum. And then we got to decide on a left bound. So I've got it somewhere there to the left of it. Move it over to the right bound, hit enter. And here we have it. According to this, at $2.47, I'm going to have my max revenue, $1,225.12. And so that is my answer here. My X value, which is P in this case, tells me the price per latte. And then the revenue I generate, the money that comes in at that price, is $1,225.12. Let's take a look at another example. Here, we're told that a farmer has 1,800 feet of fencing. He plans to enclose a rectangular region bordering on a river, which no fencing is required for that side. What dimensions should he use to have an enclosure of the largest possible area? So here we have a farmer. We've got one given, and that's the amount of fencing. And we know that we have to enclose a rectangular region where we are maximizing my area. In a problem like this, you kind of want to write down all the pertinent information and then kind of draw a picture. And you can see my horrible river over here. Let me undo that, actually. Okay, here we go. Yeah, so my raging river on one side, and then we have our land here, but it's basically rectangular. And I know I have a total of 1,800 feet. Now, I don't know if the, what the dimensions are going to be, if it's going to be longer than it is wider, or, we're not really sure, but we're just using the picture for a visual, because this will help us kind of figure this out. I know I have 1,800 feet of fencing. And if I have a rectangle, then this side, the opposite sides will have the same length to them. And so I'm going to put X there as one side. And so that makes the other side by default X as well. With a total of 1,800 then, I can write this last side. Remember that this side doesn't need fencing because it has the river there. But what 1,800 is the maximum number I have, and subtracting what I've used for the other two sides, that would be X plus X, which is 2X. So I know that this side can be as long as 1,800 minus 2X. In terms of area for a rectangle, we know it's length times width. And so in this case, X times one side multiplied by the other side. And so now I have an equation where x is one of the sides and the area is equal to the product of the two dimensions that I have there, the two dimensions that meet at a 90-degree angle. So here's the equation I can use for my area. Now this is what I want to put then into my calculator here. X times 1800 minus 2x. You can also distribute that x if you want, but you don't have to. They're all just, the same looking thing. And I'm going to go ahead and hit graph. We can see that we're going to need a bigger window here. I was using the same window that I had before. And so we need to go much longer. I'm going to go keep it at 0 for x, but maybe add another 0, or maybe add 2 zeros and maybe add a couple zeros down here too. I know my areas aren't going to be negative, so I'm going to try to look at 200,000. Sometimes we just have to play around with the look of it, and this is obviously not going to be enough for me. So let's go ahead and adjust a couple of things. I know that this could be as much as 2,000 because 1,800, right, is the limited number of x's, my amount of fencing. And okay, I'm going to make sure that I'm going to type it this way. So 2, 1, 2, 3. Whenever it doesn't like what I've done, you should be fine, but I hit 0 on my keyboard. I'm going to do this. And that's why we still weren't seeing it down here. Let's go to 200,000. Now this should work. It's drawing my function. Oops. So I still want to go just a little bit higher on my y, but I'm pretty good on my x's. I could shorten it a little if I wanted to. So maybe we were okay with 1,000, half of that. And then maybe I'll just make this into double the 200,000. Let's just make it into 500,000. Hit graph again. Great. So now yours doesn't have to have the same window. We just need to be able to see the top of my dome there. That's the key part. And so now we want to find the maximum. So I am going to hit Shift Calc, go to maximum again. Left boundary, we'll hit enter, go to the right, enter again. And then sometimes you might have to hit enter one more time. It'll say guess, and then you have to guess, but you're not really guessing. I don't know why they have that there, but for whatever reason, you have to hit it one more time. We can see our maximum here is at 450,000. I'm sorry, 450 feet for X. And then that gives me a max area of 405,000. So with our X equal to 450, the other dimension would be 1,800 minus twice that, which is 900. That gives me a total area of 450 times 900, which gives me a max area of 405,000 square feet. Let's take a look at another problem. Here we're going to try to maximize volume, which volume is the space, like three-dimensional space within a three-dimensional object. So we're told a 20-inch square piece of metal is being used to make an open box top by cutting equal size squares from each corner and folding up the sides. The length, width, and height of the box are each to be less than 14 inches. What size squares should be cut out to produce a box with, and we'll start off with a volume of 550 cubic inches. And then after that, we'll try to find what is the largest possible volume we could have for a given X. Okay, so we have a 20-inch square piece of metal. Square, of course, means the sides are the same length. So I'm going to try to draw something where the sides are the same length. This is a very horrible square, but we're going to go with it. I know that the length, width, and height must be less than 14. We're going to keep that in mind as we look at possible solutions. But we also know we want to cut equal size squares from each corner, which we will cut out and then fold in the remaining sides to give us a box top, right? So then these here will be the dimensions of the top. And we know for these, well, we know this is a 20 by 20 square piece of metal. So each side is 20 inches. And so if we're cutting a certain size square, which is going to be my X, as I look at, say, the length of this side in here, this is going to be 20, taking away 2 X's, minus 2X, and that'll be some number, whatever that number is. That'll be the width, length, whatever of one of the sides. So as I'm looking here, we want to have a volume. A volume multiplies all of the sides, all the dimensions together. And so looking at the volume for this, we would need, visualizing what we would have here, we need to multiply all the dimensions. So length, width, and height. The height, of course, is X, what we've cut out. So this is one of my dimensions, X. And then the other dimensions will be this, basically where they all kind of come together here. Well, both of these are both 20 minus 2X. So I have two 20 minus 2X's multiplied by X. So my volume formula then is X multiplied by 20 minus 2X squared. This will be the volume formula I can use to put into my calculator. So this is the equation I came up with when we wanted the volume, which is what the formula was that I found there, to be 550, 550 cubic inches. Now, I rewrote this a little bit to move the 550 to the same side as everything else so that I could set this equal to 0. When I know I have an equation that's set equal to 0, that means I'm looking for where it crosses the x-axis. And in this case, that's what I'm interested in. The x values, where it crosses the x-axis here at 0, is going to tell me what dimensions, or at least one of the dimensions, and then from that, I can figure out what the other two dimensions would be, because they're going to be 20 minus 2x. All right, so putting this into our calculator, x times 20 minus 2x squared minus 550. I hit the graph, and I'm actually I'm in a standard window here. If I want to see the whole thing, I need to increase my height a little bit there. So I need to go to my Y maximums. And let's maybe take it up to a couple of hundred, maybe take it to 250 and see what I get with that. Okay, I went way higher than I needed to. That's okay. I can readjust that. Let's make that maybe into, this is going to be my, yeah, so let's go to, make that 100, see how that goes. Okay, well, this is going to be good enough for me. What I want to find, not necessarily is the height in this case. I'm looking for where this is equal to 0. That'll tell me the x values, which give me the 550 as the specific area. I'm trying to solve this for x. All right, so going Shift Calc, what we want to find is the 0. The 0 is the place where it crosses the x-axis. So I'm going to go choice number 2 there. Left bound. So we have to go to the left of where it hits. And you can see, like, as I'm going up, it's moving slowly to the right. So if I go below here, that's kind of my left bound because it's going in a slight diagonal thing upwards. Hit enter, and then we will go upwards. So move to the right a little bit, hit enter again, and we get 2.349 is one of my zeros. So 2.349, or let's just say 2.35. And then let's figure out what the other one is. So we'll go back. We want to find another 0. We'll go to the left of this one. That's the left bound. Go to the right a little bit, hit enter again, and we get 4.43. So for those two solutions, I need to look at what they produce for the other side, because one of the stipulations we had was that each of the sides needed to be less than 14 inches. So with X being 2.35, so that's our height there, the thickness there of the box, and 2.35 times 2, subtracting from 20, right? I had this times 2 of those. That gives me 15.3. That's too big. That's not 14 inches. So 2.35 is not a viable solution. So I'm just going to X that out. With 4.43, if I go 20 minus 2 times 4.43, I get 11.14. That would be an acceptable length. And so the dimension, which would produce what we want, is 4.43 by 11.14 by another 11.14. Those are the dimensions of the box that would give us the desired volume that we were after on this first part here, 550 cubic inches. How do we do the largest possible value? Well, here we want to take our original equation here and just put a V back into it. If you remember our volume formula, we put 550 in that because that's what they wanted here. But if we want the largest possible, we just want to look at that particular function. And we want to find the maximum, right? The maximum point here, which would be the top, is what we're going for. So going back to my calculator, we've already got this typed in there, but the one thing we want to get rid of is the subtraction of 550. So I'm going to delete that part because that was not part of my original function. And we were using that to find the dimensions to get that specific area. So we just want y equals x times 20 minus 2x squared. Let's go ahead and hit the graph for this. You can see this is way off my curve here. And so we want to adjust our window once again. We need a much higher height there. So I'm going to go down here and let's see if we make this 1,000. If this is going to give me the graph I'm wanting. There we go. So what I'm after then is the max here for this. So we'll go to shift and calc. We want to go to maximum, choice number 4 here. Left bound, enter, right bound, enter. My maximum here is 3.33 with the maximum volume of 592.59. So with my one side length 3.33, that gives me the other two dimensions, which was 20 minus 2 times 3.33 is 13.34. So the maximum possible volume is given to me by the dimensions 3.33 times 2, 13.34, giving me a total volume of 592.59. And this is in inches cubed. On this last one, we're going to look at maximizing the volume of a cylindrical waste container that doesn't have a top. Picture kind of a garbage can, a circular garbage can. The diameter has to be at least 2 feet, and then the volume of 25 cubic feet is to be constructed. What should its radius be if A, 65 square feet of material is to be used to construct it, and then B, the smallest possible amount of material is to be used to construct it. In this case, what amount of material would be needed? So this is kind of a picture of what we're after. We know we want to select a cylindrical container, kind of a wastebasket looking container that's circular out the top, right? And radius R. We want to figure out, what does the radius have to be? We know that the diameter across the top here has to be at least 2 feet. Diameter is all the way across, where radius is just halfway from the center out there. And I know that the volume of my container must be 25 square feet. And what we're really trying to find here is the radius R, so that for A, if I have 65 feet of material, square feet, excuse me, of material, what does the R have to be for me to get 25 square feet? Let's look at volume. Volume is the area of the circle. An area of a circle is pi r squared. And then that's going to be multiplied by whatever the height is. If we multiply that by height, this gives me the volume, the area of a circle multiplied by the height. It's a very simple formula. We know that I want the volume to be 25 square feet. So that's 25 pi r squared h. And then if I want to only use 65 square feet of material, now we need to look at the surface area. Square feet, of course, is area, and we're using this to construct this three-dimensional. So we have 65 square feet of material. So for my surface area, the total area of what I've created, I have a circle, and the area of a circle, again, is pi r squared. So we need to take that, and then we need to add to it what would be the circular part, right, that goes around that, the sort of side here. Now, if you were to cut this and pull it apart, you would have a rectangle. So let me just draw that in. Right, if we were to open this up, right, and then think of like curling that up, the height would be h, and the length down here would be the circumference of the circle, and a circumference of the circle is pi times twice the radius, or the diameter times pi. So I'm going to just put it in terms of radius, 2 pi r. So radius, 2 r's multiplied by pi. That's the circumference of a circle. And so here, then, with the circle, the bottom part, that requires material. And then I need the material that is going to be in the dimensions of h times 2 pi r. And this would give me, adding these two areas up, would give me this total surface area, which we know we want that to be equal to 65 on this first part here. We have 65 square feet of material. Now, I don't like, and this is the problem we always run into here, we don't want to have two variables. And ultimately, we're solving this for r. We want to know what the radius would have to be. So I want to get rid of h. And I can get rid of h by using this fact here. Only I want 25 for my volume. Solve it for h by dividing both sides by pi r squared. So h, in terms of r, with a 25 volume, would be 25 divided by pi r squared. And now I can rewrite the surface area formula. This just has the r, so we're good with that. But then instead of h, I'm going to put 25 over pi r squared. Multiply that by 2 pi, oops, 2, not 2, 2 pi r equal to 65. So I don't really have this here. We have that 65 over there. Let's cancel out a few things here. I've got, this is in a numerator, right? 2 pi r. So I've got a pi, that pi can go away, and one of these r's can go away, leaving me with just 1 r. So now I have 65 equal to pi r squared plus 25 over r. And if I set this equal to 0, kind of like I did on the previous one, this gives me something I can enter into my calculator. 0 equal to pi r squared equal to 25r. So I want to plug this into my calculator so that we can find where it crosses the x-axis. If I can find the 0. And before I move on, I want to mention here, I forgot to write this in, but we subtracted 65 over here to the other side to find that. Without the 65, we just have the surface area, and we're going to use that formula without the minus 65 in order to find the smallest possible amount, the smallest surface area. We'll look for a minimum there. So with our two equations, our first one has the minus 65 here. That's because we had it over here. We had this equal to that. If I subtract it to the other side, I have this equation. This is what I want to put into my calculator, and I want to look for where it crosses the x-axis, where it is equal to 0. And so typing that in, we have pi x squared plus 25 plus x minus, 25 divided by x. Your calculator will show a division bar there, minus 65. And for a standard window, it doesn't really work. I'm just going to go ahead and pull that up here. But we can see that there's some stuff going on here. When we think about our R, that's something that can't be negative. So one of the things I could do here is, instead of having my X, which is my R, go from negative 10 to 10, we can just take it from 0 to 10. And then for my Y, we can see that it was above and below the axis. And so I'm going to go down to there. We're going to try negative 100 to positive 100. And let's see what kind of graph I get with that. This is a much better graph. And so I want to find these two places where it crosses the x-axis. Now, one thing, if you remember, that my diameter had to be at least 2 feet. These are in, remember, I went from 0 to 10. So I can interpret these as 1 and 2. This value, this solution here, is not going to meet that requirement that my diameter be at least 2 feet. If it's at least 2 feet, then my radius would be 1 foot, and this is below 1 foot. So this is the one I really want to find over here. So we're going to go Shift, calculate. We want to find the 0 where it's crossing the x-axis there. Left bound, we'll hit Enter. Right bound, Enter. And here we have it, 4.343. This would be the radius I want to get a surface area of 65. So that is my radius here, 4.343, or 4.34 if you rounded it to 2 decimals. Now let's take out that minus 65, because we want to find out what could be my the best height for me. The best radius for me to maximize or minimize, the surface area. So taking that away and then regraphing this, we see we have a very similar graph. All we did there by subtracting 65 is it shifted it below the x-axis. But what I want to find is this minimum here, because here we want to try to do the minimum amount of material. So Shift Calc, let's go to minimum this time with choice number 3. We'll go to the left of it, hit Enter, to the right of it, hit Enter. And here we have it, 1.58. And this would be my radius. That fits into what my minimum was, because the diameter had to be 2 feet. So that would be a little more than 3 feet going across. Remember, radius is half of the diameter. So multiplying that by 2, we're above 3, which is at least 2. And this would give me my maximum surface or minimum surface area of 23.6, looks like 67 square feet or square inches. And I'm sorry, this should be in feet. I have inches up here, but that needs to be feet. So we want to correct that. Sorry. Somehow I switched from feet to inches. That's not what we wanted to do there. But 1.58 feet then is the answer for the second part of the radius, which will give me the smallest amount of material.